All right. Good morning, ladies and gentlemen. I'm Nathan Lawrence. I'm here with Dalton Anderson, Connor Grass, and Jonah Koffel. We are the group behind the design of the simulated intravenous trainer. So as Mr. Tweed kind of hinted there, we are also sponsored by the College of Nursing for our project. So we got some great exposure into a whole completely different industry.
So it's kind of an overview for our project here. We're going to get into the significance of our problem that we had to solve, our first ideas, an understanding of their current systems that they use, some of our material testing, and into the base model design that we had, and then into the simulation testing that we were able to sit in with.
Looking at the significance, an IV is the insertion of a catheter into a vein on a person, and then medications, fluids, or blood can be administered to that patient. It is extremely common in the medical field. The average nurse does over 1,000 IV insertions a year, so it's a critical skill. We've got a video of what that looks like on a real person. So there's a needle with a little bit of blood in the video. So again, this is a real person. You see, once the catheter is successfully inserted, there's that little blood that travels up the catheter. That's called flashback. More into the significance, nursing students here at SDSU are trained on fake arms. These arms are very expensive, not super realistic, and they don't simulate any patient interaction because you're operating with a fake piece of plastic. The College of Nursing has sought the design of a new, inexpensive, wearable, more realistic, and cost-effective in that it's inexpensive to purchase and then maintain, as well as a device that integrates into their simulation better than their current apparatuses. So upon getting assigned our project, we met with our sponsor and we were able to establish our project main goals. Goal number one was to make it realistic and functional. This meant making sure that our device delivered that flashback effect with the proper insertion of an IV. That's when that blood can be seen traveling up the catheter upon successful insertion, giving the nursing students that visual cue that they have successfully completed the insertion of a catheter. This graphic here kind of shows what it looks like going up, and then that video also had the blood traveling up the catheter. Our design needed to be wearable. It has to be able to strap to a person's arm or the patient mannequin so that there's not an extra piece of equipment just laying around in the simulation on a table in the bed, something like that. And then cost, we need to prioritize a low upfront cost and maintenance cost to bring down the budget for the College of Nursing.
So after we established those goals, getting into some of our first ideas before we fully had an understanding with the nursing or the College of Nursing. This black section here represents the sleeve idea that we had to be able to go onto a center station or onto the patient mannequin. The red area would be the vein, I guess, path, and where that would kind of route into the skin and vein holder here down the lower forearm, which would slide into that sleeve to make it easy to maintain and change out. And then the blue area would be where the tourniquet would be applied to help simulate that practice as well.
So after we got our initial ideas kind of down, we went to a lab where the nursing students practice inserting IVs on their arms. And this was just to kind of get an idea of what the students and instructors actually liked about the arms, what they didn't like about the arms. What we found was that the arms themselves are difficult and expensive to maintain. So these arms are subject to around over 100 IVs a semester and only changed out, like replaced after 2 years. So what that means, the reason that they're only changed out every 2 years is because they're so difficult to do in-house. Like the skin is so tight that you can't peel it off and put it back on very easily. And this needs to be done with all 11 arms at SCSU. So towards the end of the life cycle of these arms, there would be holes from previous IVs left in them, basically outlining where like the veins themselves are. So that kind of takes away from the realism, because in real life you're not really going to be able to see these veins very easily through the skin. And along with these holes, they they tended to make the arms vapor lock. So what would happen is that air would get into the tubes and basically block the flow of blood. So when you actually insert an IV into the arm, it wouldn't actually give any flashback. So you wouldn't know if you were in the arm, in the vein, or if you missed, or kind of what was going on. So, and I'm breaking down the current arms that they have, the NASCO practice arm. So this arm, skin wasn't very realistic, so it had more of a rubber feel. So if you were to just kind of touch the arm itself, you would definitely be able to feel that it's not very similar to human flesh, I guess. So as well as it being rubber, it was very tendon, very prone to like leaving holes. So this was the main offender of where, like, seeing where the veins are on it. Similar to the NASCO arm, the medical X practice arm. The skin on this one was a lot more realistic. It was more of a silicone-based skin, so it was more transparent, felt a little bit more realistic. Something that the college of nursing didn't like was that the reservoir bag wasn't very big, so they would constantly need to be refilling it during simulations or lab, which was something we took into consideration. And with the mannequin itself, so the college of nursing purchased 2 of these mannequins in 2016 for $40,000. Currently, to replace them, it would be well over $100,000. So due to how frequently the college of nursing actually uses or basically trains IVs, they don't want to damage these mannequins. They don't want to have to replace them, and keeping them clean is very difficult. So they are able to have blood flow through the arms, but they don't do that because it's so difficult to keep clean, make sure there's no mold, and with how much they're used, they would be replaced very often. So with the current apparatuses understood, having a background of what they like and what they don't like, we get into our material testing. So for the veins themselves, we had 4 different thicknesses. 2 of those thicknesses, I think one of them was about 1/8, and one of them was about 1/10 or 1/10 of an inch. Oh, sorry, 1/16 inch thickness for the latex and 1/10 of an inch thickness for the latex. Whereas rubber was a little bit thicker. And for the skin, we had 2 materials and 3 different thicknesses. So silicone, 2 millimeters, and 2 different thicknesses for the rubber. Kind of getting into what we actually tested. So what we were looking for in the veins was how difficult was it to actually insert the IV into the vein itself, as well as how durable were these veins, like how many IVs could we insert for failure. What we found was that the 1/2 inch outside diameter, about the 1/16 inch thickness tubing performed the best. Some of the comments we got about it were that there was a realistic pop. It felt like you could definitely tell you were actually inserting into a vein. And they were pretty comparable to the current arms that they have, as well as it being fairly resistant to leaking with large amount of pressure. So getting into the skin, we found what we were testing was that the skin it felt realistic. You couldn't quite see everything under it, but you could kind of see a little bit. And then kind of how difficult it was to, again, pierce through the skin into the veins. And what we found was that the 2 millimeter thick synthetic silicone skin, tattoo skin, was the best. It felt realistic, very elastic. After multiple piercings, you wouldn't really be able to see where the IV was inserted. And it was on par with the current apparatuses, so I felt like it was very applicable.
So after some of our personal testing there, we were able to bring our skin and vein combination findings to the College of Nursing. where they were actually able to test in a more similar setup to how they would be using it in their labs. So that bottom right picture there is connected to the blood bags that'll be used at a more similar setup to those labs. We were able to test the skin and the vein combinations. In that top left picture there, you're able to see the flashback that we were able to get through these skin and vein combinations. And back to what Connor was saying there, we were able to get that feedback from that real pop feel that you get with a real IV during this material testing. So after this, we're able to take these findings and go more into the base model design and kind of integrate the whole system together.
So after having our sponsors check out our selected materials, and observing their current apparatuses, we were able to make a decision matrix. The weightage, we gave each category a weight from 1 to 5, 5 being the best performing or the most important, and then 1 being the least important, and then scored each individual apparatus in each category from a scale of 1 to 5, and then multiplied those two together to get a score. As you can see, our model on the far right side of the screen, the sieve, outscored the current apparatuses. So we were confident moving forwards with our selected materials, proving that they were going to successfully provide the realistic simulated environment for the nursing students.
So now that we had our materials selected and we knew what the College of Nursing wanted for their model, we started developing SolidWorks models of what we thought that it might look like with various size and skin paths. These first couple models were just to kind of get an idea of what we wanted. But then in our next models, in Mark 4 and Mark 5, we made full prototypes that did incorporate skin clamps, either integrated with the 3D print or external with the binder clips. These are the 2 prototypes that we brought to the expo at the end of last semester.
Awesome. At the expo, we had some great success. We got 3rd, and then we got some excellent feedback from our judges. Our judges liked our design. However, they wanted to see it, some improvements. They wanted it to be more professional. They didn't like the look of the binder clips, and they wanted to see it a little bit more ergonomic and stable. The Velcro straps we had weren't fastened securely because they were always kind of a temporary part of our design. So they encouraged us to look into the ergonomics of how it actually sits on a person's arm, and then making the Velcro straps more secure and able to be fastened.
So moving into second semester, we kind of agreed that the successes we had were that we were able to get consistent flashback. That's something that the previous models couldn't do, so we called that a success. And so defining our primary goals going into second semester, we wanted to improve the skin clamps, making sure that they were securely fastened to skin to the actual model, as well as were easy to take off. And then we wanted to make some quality of life improvements to the model, making it more comfortable to wear, making it sleeker, just all around, just improving it. And then improving the actual mounting to the arm, making it more comfortable, the straps that we use. We kind of tinkered with those a little bit and played around with them. And then finally integrating the sieve into the actual classroom setting, making sure that the transition from the previous systems to our new one was pretty seamless.
So with some of the advice that we had gotten from the expo and that we wanted to go into the second semester with, we made some conceptual designs that incorporated a sleeve, which we've been talking about since the beginning of the project. We also tried some new clamping devices with the binder clamp covers. And then we also have a slot, so that way we could make the veins much easier to install, so you don't have to thread them through the holes.
We then had a sponsor meeting after we created 3 different patterns for a sleeve. Once we met with the sponsors and discussed moving forwards with the sleeve, we all realized that the sleeve would be harder to maintain. It'd have to be cleaned and washed in between labs because of the spilling of the fake blood, would probably get stained, and then making them and making new ones in the future would be difficult. So we reverted back to the Velcro strap idea and decided to move forwards with that.
So going back to the Velcro straps, we did also decide that they needed to be fixed more securely. So now they're fixed with screws instead of just going through a loop. But one of the really big changes we did was the skin clamp mounts. We now use a compliant band that goes over the whole edge that has pressure over the entire edge, so it's better clamping. It's also much sleeker than the clamps that stuck outside of the model. It also allows tape to go across those clamps for better adhesion.
So after that new design there, we brought that back to the College of Nursing and wanted to get some testable numbers. We estimated that there's going to be about 240 punctures per year on these devices. So we needed to make sure that our veins and skin would hold up to that, or how often we had to change those out. In a sporadic testing here over a 4-inch section, the skin and veins were able to hold up to a leaking fluid with the clamped veins on the veins. And then in the concentrated area here in a 1-inch section, again, it was able to hold the fluids up to that 200 punctures with the clamp system.
After doing our final durability testing and meeting with our sponsors one more time, they felt comfortable integrating our device into the real simulation. So this was integrated into the actual nursing student simulation, and actual students used it in their simulation. The findings we had from this, in that picture there, you can see the veins coming up out of the device get in the way. When nursing students were trying to put on a blood pressure cuff or maneuver around the mannequin, the veins were in the way, and then the ring stand that the blood bags were on was in the way. We did achieve our flashback goal of 100%. Every time a nursing student successfully inserted a catheter into the vein, there was successful flashback. And then the clamps that we had on this device were too tight. When wanting to change out the skin, the clamps were much too tight, so we had to review that part of the design.
So trying to incorporate some of those changes, we added a vein redirector. This you just slot the veins in them, and then it snugs right up to the base model. We also changed the clamps, which is one of the significant changes. We added a handle on the end, and we messed with the ledge distance, so that way it would be much easier to pull off. Then we also changed how we mounted the Velcro strap. So we used a new type of Velcro that sticks to itself, which allows it to be tightened all the way on a human arm, which is much smaller than mannequin arms, but can still go all the way up to the mannequin-sized arm.
We took this new design into the second set of simulations here, where we were able to use this on a standardized patient. One of our goals was to have that wearable aspect for this situation specifically. You can see here our device strapped onto the standardized patient, who was able to then move around and still continue all of the other practices in this simulation lab. And then back onto a mannequin here, you can really see the vein diverter being used here properly. It kind of gets the veins out of the way and can kind of tuck them underneath everything. And it really doesn't affect any of the other duties that the nursing students had to perform in these simulation labs, as well as the new clamp system. You can see there made the material changing in and out of the skin and the veins much easier.
So we just want to recap the final design. We have the 3D printed base, the 3D printed clamps, along with the 3D printed vein redirector. And then we have the purchased components of the skin, the vein, the Velcro straps, and the screws for mounting it.
Going into a cost breakdown, the 3D printed parts, $3, Velcro, $1, screws less than $1. The skin sheet is where most of the investment is at, because this skin is ordered from a third-party company. And then the vein is also very inexpensive at only about $2.40. And that is 8 feet of vein, which only 4 feet is needed for the device. And then you can have an extra 4 feet to replace. So the total product comes out just under $25, which is a significant reduction from the current apparatuses.
So to review some of these goals and go back to a comparison here, you can really see the integration into the standardized patient model here. Previously, they would just have the third arm sitting on a table next to the standardized patient. And while the standardized patient is able to wear ours, it's a much better integration into the hospital environment in that simulation setting that they were looking for. As well as the realism, along with the flashback, this is how they have the arm set up before in the mannequin bed. Obviously, the third arm in the mannequin bed is very unrealistic and really kind of took away from the simulation setting. When we were able to strap our device onto the mannequin, it was really seamless and integrated very well into the realism of this simulation setting that they had. And then along here with the performance of the flashback, we get very similar results, if not better flashback compared to the ARM system that they had running previously, where ours excels significantly from the other design. Is they were getting about 50-50 results on if they would receive flashback due to that vapor lock that we talked about earlier. And like Nathan said, we've received 100% successful flashback when the IV has been inserted properly. So you can really see the flashback comparisons there.
So to put some numbers to those qualities, we have a student survey for both the performance and the realism, in which the student survey reveals that we're about 34 and 36% better than the previous models. And then when we go to integration, pretty much just the size that it takes up, we're like 88% smaller, which means it integrates much better into the simulations. And then convenience, when we're talking about time, it's about 50% faster to replace this, to set it up for the simulations. And to replace the skin and veins, they have to ship it in, so it's over 24 hours versus we can do it in 5 minutes, meaning that we have over 99%, it's over 99% faster. And then when we go to cost, going down from $1,000 to $25 means that you have like 97% savings, along with 88% savings when it comes to the yearly maintenance.
So to really hammer back in on the goals here, the realism goal that we had, achieving that 100% successful flashback was something that we really wanted to reach for, and we believe that we have achieved that goal. The integration and the wearable aspect of our system onto a standardized patient and the mannequin was also achieved. And then with the cost savings that we just recapped, with over 97.5% cost savings from our product to the systems that they were currently using, we believe that we have provided the College of Nursing with exactly what they were wanting and the change that they were needing for this simulation setup. Does anybody have any questions?
I'm a little confused about is it single use, or you said you had a 200 puncture? How many times can they use it before they have to replace the base?
Excellent. So the question was, how many times can our device be used before they have to replace it? So the goal was to have our design only need to be replaced once a semester. So at the end of a semester, the staff can go in and just throw in a new vein and a new piece of skin super quick. Does that answer your question, sir?
Well, yeah. So it doesn't leak after the first time?
No, sir, it does not leak. It does not leak. The latex rubber tubing of the veins holds up very well against those pokes. It's not self-healing, but it's tight enough so that the small needle holes close on themselves, and there's not enough pressure in the veins to cause a leak.
What happens though if you accidentally hit a previous hole? Anything?
With the concentrated testing, we poked it 200 times in that 1-inch section, and we were able to see that with that it does not leak. So, and it's very difficult to poke in the exact same hole.
Oh, I know, sure.
Yes, ma'am.
What's the size of your guys' simulated vein compared to a human vein?
How does the size of the simulated vein compare to a human vein? The simulated vein is a little bit bigger, but being set down into our device, it feels similar on top through the skin. It's raised up a little bit, and the nursing students get the feel of the vein through the skin is similar.
Your blood pressure measurements, it looks like you're using maybe 14, 16 inches water column. Is that fairly realistic with the blood pressure in your veins?
So the question was, is the pressure in our device similar to the pressure in a regular vein? The pressure, since we were trying to achieve that flashback, we're not quite using 16 inches. It's, you know how many milliliters it was in each blood bag? I think it was a little less than 200 milliliters in each blood bag, so probably 400 total in the system. So the pressure was never measured, but through our testing iterations, we were able to get that consistent flashback without leaking, which achieves the goal of the flashback.
Remember when I got the opportunity to judge you guys, I mentioned a commercial market for this, since it is such a cost-effective solution to compare to what's out there. Have you looked any more?
We have not looked into marketing this product or establishing a company. That could be something that we could, the College of Nursing could look into moving forward with this device, though.
Thank you.
Thank you very much.